time to start the show. Well, not much of a show, just a lecture. Anyway, so last week we covered array basics as well as sorting algorithms. Insertion sort, quicksort, we are kind of half cooked with quicksort. And in this week, well, technically only today's lecture, because tomorrow is going to be a public holiday. And by the way, we won't have workshops for tomorrow either. That's actually the reason why we start the workshops on Friday of week 1, such that the ones who have a workshop on Friday, they didn't really miss a workshop. Anyway, now in today's lecture, we'll continue to finish talking about quicksort. After that, we're going to start talking about strings, which is essentially no more than a special kind of arrays that are used to store characters. That's the main topic of today's lecture. Now, before we move into the technical content, I just want to quickly remind you that our mid-semester test is coming. We scheduled that for Friday in the Friday lecture time, 12:50 on 12th of April, which means it's the week after the non-teaching week, so you still have a couple of weeks to prepare for that. Don't miss the mid-test. I suppose there are two main things that I want to mention about this mid-test. One is our class is actually quite large. We cannot fit everybody in the same exam venue. What we did is we're going to place you in two different venues, one in the Wilson Hall, the other is in the Quanley Doe building. And make sure that you check your student ID and know which room you should go to. That's one thing. The other thing about the exam coverage. Basically, the exam coverage is to cover what we have taught up until last week. We cover pretty much most of chapter 1 up to chapter 7, except for strings, which is the content for this week, and it's not going to be in the mid-test. We covered sorting, some algorithms, algorithm correctness and efficiency analysis, some integer binary representation. Those are in chapter 12, part of chapter 12 and chapter 13 of the textbook. These are also already covered, and they could be in the mid-semester test. Two main things. And we actually have released 2 past tests from 2021 and 2022, and a sample test for your reference to prepare for the mid-test. The past tests, they are prepared in a sort of slightly different setting. They are like an online open book test. This time we have a in-person closed book test. So test 1 and test 2 probably not that relevant. Past tests 2021 and 2022 probably not that relevant, but still you can have a look at least the difficulty level would be very similar. We're trying to keep a similar difficulty level across different semesters. Now the sample test here would be probably the most close to the actual test in terms of format, and here I want to quickly show you what you're going to expect in the coming mid-test. It's going to be a 15-minute test, 5 minutes reading, 45 minutes writing. Make sure that you be there on time, because we only got the room for that limited time session, and other subjects might be also using them. We cannot really just keep the room for forever, and we cannot delay the start of the test. The mid-test is worth 15% of your overall mark of the subject, and as we just mentioned, it's a closed book. The only thing pretty much allowed is the writing materials. You can bring pen, pencil. Pencil is fine, but not calculators or books or any study notes. You should read a few of. You should also read these exam instructions. The actual test will pretty much share the similar instructions, such that you sort of save a little bit of reading time. The test will have 3 questions. First 2 are writing some code and related something to functions, because we have covered this. And then potentially a recursive function. This is one of the sample questions in the actual test. I cannot promise you whether you will see a recursive function or not. It's covered, so it's examinable. The last question has something to do with algorithmic analysis. Because we covered that in the last week, so it's also examinable. Overall, it's not supposed to be super challenging, but you need to prepare for it. Don't get too comfortable saying that I've come to every lecture, I'll excel in the mid-test. Not like that. C program language ultimately is a language, and when you talk about language, you have to speak and have to practice it. Otherwise, you are not going to really master it. So do the test, do the textbook exercises, do the online exercises on our system. and get ready for it. Any question about the mid-test? Anything at all? If it's all right if you don't have any questions. Main point is really you have to prepare for it. Don't get too comfortable. So let's come back to talk about Quicksort. Quicksort, we talk about the idea of it. We also demonstrate the procedure of Quicksort. Let's just do a quick flashback. What does Quicksort do? The core idea of Quicksort is we don't want to get the whole thing sorted, or we don't even want to find the correct position for any particular element at any particular point. Instead, we try to do the sorting in multiple iterations, and we want to sort of, in every iteration, we make the whole array in a trend that is closer to a overall sorted trend. And after a few iterations, if we made the array in the right trend for every fine-grained level, then the overall whole thing is sorted. So that's the idea. So here, this wave here basically shows the different elements values. So obviously, if you just got a random array, the values of the element in the array is going to be up and down, like they are not in order. Our ultimate goal is to sort of reorganize these numbers in this array such that they form this overall increasing trend. That's the great goal of sorting anyway. And to do this, the Quicksort ideas. Well, let's partition this array into 3 partitions, and using a special value that we choose that called the pivot. There's some sort of choosing strategy for choosing the pivot, but none of them are like perfect. It's more of them. They are all more or less like a heuristic choice. There's no perfect choice, and we'll talk about it a little more later on. Now, so suppose we just pick the first one as our pivot. This is what we did in the last lecture anyway. And what we're going to do is we're going to use this pivot value to pretty much reorganize the whole array into 3 partitions. One of the partition is the elements that are all equal to the pivot, and we put them in the middle. And all the elements that are smaller than the pivot, we put it to the sort of first half of the array. And all the elements that are greater than the pivot, we put them to the final, like the second half of the array, or the final half of the array. Now, once this is done, because we know everything in here are smaller than these pivot values, and everything in here is greater than this pivot value, then we actually got the correct position for the elements in the middle, and we don't need to worry about them anymore in the later iterations. All that we need to do is that later we now have 2 halves of the array. Each of them are again in the initial unsorted manner, and we need to repeat the previous sort of partition procedure on these 2 halves, and to make each of them in a sorted pattern. And after that, we just sort of logically think that we piece this first half and the middle half and the third half all together and form the final one. But all of these are what we call in-place sorting, in the sense that you really don't need an extra array to hold these extra 2 halves. They are just all keep in the same array, except that we use these 2 variables, fe and fg, to keep track of the end of the first half and the starting point of the second, the larger than half. And fe here is the first equal that we show in the last lecture. And fg here is the first greater. First equal means the first element that is equal to the pivot. First greater is the first element that is greater than the pivot. And this points to the starting point and the end point of these 2 less than and greater than partitions. So far so good. Now, let's look at the code. How do we implement this process? Obviously, in the slides, it also contains this piece of code and a lot of this correctness proof. I'm not going to worry about it. I'll just sort of directly move into the actual code such that it's a bit easier to see the big picture. The correctness proof obviously is also important, but you can read it after the class because you know how to prove the correctness anyway from the last week's lecture. So we again look at the code together with the demo that we used from last week, such that the code and the action correlates a bit better, and we can know how really it works. So the implementation here says, let's implement a quicksort function that takes an array of numbers. This array has like 11 numbers. This is essentially the size of the array. Takes the an array and its size, and we're going to run a quicksort. And this array here essentially is just a copy of the array that I have in there. So it's going to call the quicksort function, and it's going to print out the sorting result after calling the sorting function. So none of these are super interesting yet. Let's move into the actual implementation. So the actual implementation says, well, we say we want to do a quicksort, and to do the quicksort, we know we need to do a partitioning. And to do the partitioning, we need to choose a pivot. So we are going to use a variable called pivot to recall which is your pivot value. In this case, our pivot value is chosen as the first element, 33 anyway. In the implementation, we actually created a function just to choose pivot, such that we have allowed a bit of flexibility. How do you want to choose a pivot? In here, we actually have 3 different implementations. We can always take just the first element in the array that you want to sort as the pivot, or you can take always the middle element as the pivot, or you can take a randomly chosen element within the array as your pivot. Here, the rand function is just a function that returns a random number, and by modding n, it can limit the random number to be in the range of your array size. That's just what it does. So after we choose a pivot, we are going to run this partition process, and the partition process will take over the array, sort of run a pass on it from the starting element up to the nth element, which is n here is again the size of the array, so up to the end of the array, and it's going to calculate. It's going to take the pivot as the input as well, and it's going to calculate where would be that first equal variable is going to reside, and where is the first greater variable is going to reside, because these are the 2 variables that tells us which are the ending point of the first partition and which are the starting point of the third partition. Right? Make sense? So far so good. And the reason why it needs to put this ampersand into it is because this is the way that we pass a pointer into the function call, such that the change to this first equal and the first greater variables in the function call will persist when the function call finishes. This is the way that we can actually update the first equal and first GT variables. And after we got this first equal and first GT, we can recursively call this quicksort function on the first half and the greater than half. So the first half is still starting at the original starting point of the array, and there are this first equal number of elements, because this is the pointer pointing to the, if you look at the slides in here, this FE is the first equal variable in here. So you can see after the partitioning process, FE actually points to 1 element after that. And 1 element after this first partition is actually the size of the first partition. This is consistent in the initial call of the quicksort. We actually need a number that's actually larger than the last element's index. So at the beginning, we know we have 11 elements in here, and the last element would be just numbers 10, right? The last element would be if you put it in a subscript index, the last element would be, so this would be numbers 0, numbers 1, and numbers 2 up to numbers 10. But in the function call, we actually need to put 11, which is the size of the array. And the same thing happening here. The array and the size of the array, which is a number just greater than the last element's array index. Now, similarly, for the second half, we need to figure out where does it start. And apparently, for the second half, will be the array plus first greater. Array is a pointer. Remember, arrays variables are just pointers. And pointers can do pointer arithmetic. And if you do a plus first greater, it will give you a pointer pointing to this position. Now, where does this array end? Now, you can't just use n as the ending place, because you actually don't have so many elements in this array. The number of elements in this second half is just n minus fg. So this is the size of the second half. This is the starting point of the second half. And this is starting point of the first half, and this is size of the first half. And we do this recursive processing. Make sense? This is the overall process. And it's not super complex yet. The real challenge is really the partition implementation in here. how do we sort of implement this process that we demonstrate in the last lecture to move the elements based on whether they are smaller than the pivot or equal to the pivot or greater than the pivot. Now, this is the core part. We have this next variable to go through next numbers in this array. The next variable works on that. And fg again is the sort of first greater than looping variable to go from the right to the left to keep track of which is the starting point of the greater than partition. And when we say if we have go through the elements from left to the right and I've hit the greater than partition, then I can stop. This is the stopping condition. Because I know everything starting from this greater than partition will be greater than the pivot already. So I don't need to look at them any further. So the next looping variable will go from left to the right. And once it hit this greater than variable value, the loop will stop. Does this part make sense? Well, if it doesn't, it's okay. Gradually, it will make sense after we demonstrate a few iterations. So the key part is really we keep comparing the item pointing to by this next variable with the pivot value. So this is really the key operation that we need to run in each iteration. Keep comparing the element pointing to by next and the element stored in the pivot, starting from the first element. Because we chose the first element as our pivot, so in this case, they must be equal to each other. So they must be equal to each other. And according to our rule in here, it says that if the current element pointing to by the next is smaller than the pivot, they should be moved to the left-hand side of the pivot. If it's greater than the pivot, it should move to the right-hand side, to the greater than partition. Now, if it's equal to the pivot, or this branch, the final else branch, is the equal case. This is the less than case, greater than case, and this is the equal case. When it's equal, we don't need to do anything else. All that we need to do is, all right, I know the first element is checked. Let's move on. So first element is done, move on. Now, when we move on, again, we'll compare this one with the pivot value. And this time, we got a value that is smaller than the pivot. And when we got a smaller than case, it's like this. The smaller than case says, let's swap this smaller than value with the first equal element. Because we say the first equal element is the element which we guarantee that is equal to the pivot. And if we have an element that is smaller than that, it must be moved to the first half. Yes?
Is that outcome function returning 1 or negative 1 based on the result?
Yes. Comparison function is a sort of a C program's sort of standard procedure that compares two elements. If the first element is smaller than the second element, returns a negative value. First one is greater than the second one, returns a positive value. If the two are the same, returns 0. That's standard procedure. But you have to implement this comparison function on your own because depending on what kind of different type of data you want to compare with, they might have different comparison criteria. And even if you just want to say, what does it mean by smaller than? If you want to achieve an array that is reversely ordered, like sorting from the greatest to the smallest, then you might want to say, if the first one is greater than the second one, you want to return a negative value. If you just change the comparison function, you can already change the whole sorting order. So that's the reason why we use a comparison function, and this offers the flexibility to configure how you sort different type of things and exactly what order you want them to be. So that's the comparison function. And this time we got a number that is smaller than the pivot value. So what we do is we swap the two. Here I use a variable to help us do the swapping procedure. In the code implementation, there's a swap function that Shannon also previously have shown you how to swap two integers using a function call. You use their pointers. And here, because A is a pointer, A plus something is still a pointer, A plus something is still a pointer. This is just pointing to the first equal element and the current element that we are checking. So we swap the two. And according to this rule here, I know the first equal element is still this one, and the current element we are looking at that is smaller than pivot is this one, so we are going to swap them. After swapping, the code says, all right, after we swap, we know the first equal element is not the previous element anymore. I have to move that. Because I've done this swap, and the first equal element previously stored in here, which is this element, is not really equaling to pivot anymore. I have to shift that forward, and so first equal got +1. This becomes 1, and because of that, we actually, this smaller than partition actually has grown. So now the smaller than partition has grown, and also we are done with processing this element 1. We need to move on to the next element 2, so we are going to increase this one. So this one is also done. I'm using a yellow color to represent the current equal partition that we found so far, because we haven't seen any of these things. When we haven't seen it, we assume that they are actually the equal partition. The blue color is the less than partition, then the green color is the greater than partition, and the red color in the subscript indexing for the array elements, they are representing the element that we have seen, so we have processed so far. Right? So then we move on to this one, and let's look at what we have. And 55, this is the case where we got a greater than. And according to this greater than row, greater than branch, it says that, well, if we got a greater than element, we have to swap this current element with the element that is pointed to by this fg. But before we can do the swapping, we have to reduce the fg value by 1. Why? Because fg, you see, here starts at 11. And 11 is actually beyond the boundary of the array. So we have to reduce that a little bit. And let's reduce this one to 10, according to the coding here. And we got this one. So we now actually got a greater than partition that has sort of also grown into the array. And we're going to swap the two. And when we do this swapping, I don't actually need to check what's the value in there. I'm just going to blindly swap that. And I'm going to put that to the end. I'm not going to worry exactly what's the value in here. I don't know whether it's greater than the pivot or smaller than the pivot. I don't care. All that I care is that I know I found an element that is greater than the pivot. So no matter what, I'm going to take out the last element in here. I'm going to put the 55 to the end. So that's the greater than process. Now, as you can see, because we haven't really looked at this element, so at this moment, the next element to process cannot move directly to the element 3. We have to again look at element 2. So that's the reason why in this greater than branch, not like the equal or less than branch, the next variable hasn't got grown. So we have to again look at this one. Make sense? So we will now have covered the 3 branches and keep repeating this one because we showed that the process in the last lecture. I don't want to bore you and repeat the whole thing again. These are the 3 key branches, and importantly, in each of these iterations, if you look at the value of next and the value of fg, you can see that in the 3 iterations that we've demonstrated, in the first 2 iterations, next got increased after each iteration. In the last iteration that we demonstrated, fg got reduced by 1 in one iteration. So in general, if you look at these 3 branches, in one iteration, either next got grown by 1, or fg got reduced by 1. And how many times next can grow until it hits fg? That's just fg minus next, right? Each iteration, next will grow by 1, or fg will reduce by 1. How many iterations do we need to make next meets fg? Suppose I'm starting at this row, okay? Now, if one of you is sitting at the end of the lecture theater, right? And in each iteration, either I move up by 1 row, or the other student move towards me by 1 row. How many iterations do we need to meet for the 2 of us to meet? Suppose there are in total 20 rows.
20.
Then at most we need 20 rows to meet, right? Yes?
N on 2.
Yeah, sorry?
N on 2.
N on 2? Really? So suppose the other student at the end doesn't move.
Only move down one step or move up one step.
So in each iteration, either I move or the other student moves, right?
Or either.
Right, not the same, not at the same time, right? So if there are 20 rows, the work I need to do is the other student doesn't move, I'll just keep going and going, and after 20 iterations, we meet. So that's the idea. This is the sort of complexity analysis for this while loop. How many iterations do we need for this while loop to end? So essentially, all that we need is just fg minus next. Because next starting at 0, which is this end of the lecture theater, and fg starts from the other end of the lecture theater, and they meet by fg minus next. And that's just the size of the array. So for this partition function to work, we just need, in the worst case, O(n) time to run this partitioning. And it doesn't need to be, even though we never really say, like in a for loop, you go for I starting from 0, I less than n, and then I plus plus. We know if we write a for loop like that, we know exactly this is O(n) time. In this while loop, we didn't write it in that way, but we can still analyze that for this while loop, it takes O(n) time to complete. Make sense? Now, that's Quicksort, and we also demonstrate this process. Now, after one iteration of going through the whole array, we can partition it into 3 partitions. And after that, we only need to look at the first partition and only need to look at the smaller than partition and the greater than partition. The equal partition, we don't need to worry about them anymore. And then we're going to look at the smaller than partition and greater than partition. And the same principle applies. When we look at the smaller than partition, the max we need to look at is just this number of iterations. Here we got like 5 elements. Then we only need 5 iterations to get it done. Here we got 3 elements. We only need 3 iterations to get it done for further partitioning these 2 halves separately. Now, in a sort of rough generalization, if we don't worry about this sort of equal partition, then in each round of this recursive partitioning, we only need to look at one element one time. So each round it takes O(n) time, each round takes O(n) time, even though technically this one doesn't really need O(n) time because the equal partition can save that time. But let's be generous and let's just throw in this equal partition into the time calculation as well. So this is also O(n) time. Repeatedly, this is also O(n) time. This is also O(n) time. Obviously, it's smaller than O(n) time, but we say big O notation is upper bound, right? So it's fine. We can throw in O(n) time. And this one is also O(n) time. So the analysis of this process is really how many O(n) time do we need? Then we know what's the time complexity of this quicksort algorithm. In this case, apparently we got a total of 5 rounds, and we got 11 elements. So this doesn't sound like a log(n) rounds. If you think about log(n) rounds, we got 11. If you take log base 2 of 11, what's that? What's log base 2 11? 3-ish, 4, no, somewhere between 3 and 4. When we cannot do 3 point something round, it's either a whole round or nothing. So let's say 4 rounds. But here we break that promise. We actually go beyond 4 rounds, and it takes about 5 or 6 rounds to get the whole thing done. And the reason for that is, in this partitioning process, we did not always got a balanced partitioning. Remember, if we can do this binary search process, we can break an array into perfect 2 halves each time. Then there are just a total of log base 2n times that we can halve it. But in this case, it's not like that. The issue is, for example, in this part of the partitioning, unfortunately, when we pick the pivot, we pick the first element that actually break the array into 2 really unbalanced partitions. One partition has only 1 element, the other partition has all the rest of the elements. So in this case, we are not really saving anything. If in each of these partitioning process, if in each of the rounds, it always happens like this, we always pick an element that only cut the array into 1 element and the rest. How many iterations we need to do if we do that? How many rounds of partitioning we do? Really? What's your thought? Any thoughts? Yeah?
I'm shaking it because I'm getting confused.
Okay. No, that's okay. Anyone else? Yes? Yeah, then we need n rounds, right? Think about an array. Here, let's not worry about all of these things. Let's pretend all these things don't exist. Let's not worry about all this. Just think about, suppose this is the array that we have. Now we want to run this quicksort algorithm, and we chose the pivot of the first element in here. So after one iteration, we will cut this array into two halves. And one half has only one element. The other half has still 4 elements, which is n minus 1. So in one round, we only fix one element. And there are still n minus 1 element that we have to run quicksort on. Now, in this second iteration, obviously we are quite lucky. But if I break this one a little bit, in the second round, instead, if we don't have like 18 and something, instead if we have this 29, 16, 19, and 18, then in this second round, I'm going to partition this array into a 29 in here, and all these other elements will be in here. And the 3 elements in here, they will not be sorted yet, right? Maybe I'll sort of polish this one a little bit, make sure that the colors match, then it might be a bit easier to see. So the first iteration, we are all good, right? One element of one half, the other rest of n minus 1 elements on the other half. Now, this is the second partitioning procedure. We are again picking the first pivot in here. First element is pivot. And apparently, when we use this first element as the pivot, we are going to cut this array again into two halves. And we will find the correct position for 29, and we know that it should go to the last position in here. But the rest of them, they will stay as the less than partitions. So this is what will happen, right? First round, in the first round, we fix one element. We have 4 elements left. Second round, we fix another element. We have 3 elements left. So each round, we only fix one element. How many rounds in total we need to do to get everything in place? N rounds, right? And in each round, we say, in each round, you already take n iterations. The total times n squared. That's the worst case setting for quicksort. So that's the reason why we say when we run quicksort, it's really important to choose the right pivot. If you have a magic method or have an oracle that always tells you that is the median value of the remaining of the array to sort, and you always take the median to do the partitioning as the pivot, then we are going to achieve this binary kind of partitioning. And we got this binary partitioning, we are going to get n log n time for quicksort. If not, and if we are unlucky, we always pick a pivot value that cuts that they partition the array into two halves. One is one element, the other is the rest of the array. Then we are going to end up with O(n) squared time, and that's not great. So that's the quicksort. And the discussion there, this is just the code that I show you and a bit of a short statement to show its correctness. It doesn't really matter. And this is the runtime analysis for the partition algorithm, how we show it that it takes O(n) time to run one partitioning, right? This is the overall runtime, and this is sort of the lucky time. If we are lucky, if we only get one element, then apparently only one comparison, that's it. If we have more than one element, we need to go through the whole thing once to do the partitioning. So this O(n) time is to go through the whole thing to do one partitioning. After one partitioning, you got it into two halves. And for each of the one half, we need to repeat this quicksort solution, and Quicksort takes this Tn time. Tn operations, not really Tn time, Tn operations. So we got two halves. Each of them has the size of n over 2 in a perfect world. And you need to do that for twice for the two halves. Make sense? So this translates to n log n time. Now, in the worst case, this is what will happen. Given n elements, we need to go through them one time. And we end up with two partitions, one with only one element, the other with all the rest of the elements. And this will translate to the O(n) squared time. Now, in reality, it's somewhere in between. So do this somewhere in between kind of analysis, like if you have, so, oops. So what does this somewhere in between mean? What does this term mean? Now, the first n value in here, you know, it's still just n operation to go through the whole array to do the partitioning. But what does this mean? What does this mean? This is actually an average case analysis. What it says is that now, given a pivot, this pivot can partition the array into many different cases, many different possibilities. One is that, so suppose the first row of the chairs is the array that I want to partition. After I chose a pivot and I do the partitioning, the worst case is that I'm going to partition the array into one chair and the rest of the chairs. I could also partition the array into one chair and then all the rest of the chairs. And then two chairs and the rest of the chairs, right? Each of them, suppose that we have the equal probability of all these cases to happen, then this is the case to sum them up. And why there's a 2 in here? Because as you can see in here, this is T0 plus Tn minus 1. This is just that adding. So each of these is just basically, because you go from I equal to 0 to n minus 1, right? So this is T0, T1, T2, T3, T4, T5. And this part can be T0, T1, T2, T3, T4, T5, T6 up to Tn minus 1. And this second half can also be Tn minus 1, n minus 1, Tn minus 2, Tn minus 3, and back to T0. So each of T0 or Tn minus 1 can appear twice in this calculation. Basically what I'm saying is that this pivot can cut the array into 1 and the rest. It can also cut the array into 1 and the rest. These two are actually symmetry to each other. That's the reason why in this term, there's a twice in here, but in the previous equation, there's no 2 in there. Now the n in here says that, all right, on average, each of these cases could appear 1 over n times. Because if you have n different cases, each of case can appear one of the cases, right? So you have to take the average. That's the analysis, how we got to this point. And this point translates to a bit higher than n log n time. Don't ask me how to do this translation. This is not sort of beyond the scope of the subject. If you want to know, come do more computing subjects with us. This one?
Yeah.
Not really. Natural law is not 1.44. Not that either. but if you really want to know, do another algorithm analysis subject with us. So far, so good. If you're really sort of confused on what's going on here, don't worry about it. Essentially, what we are saying is that for Quicksort, the best case you can get is n log n. Worst case is fall back to n squared. On average, it's somewhere in between. And this is where the somewhere in between means. Any questions? Yeah? All good? So far, so good? That's the Quicksort analysis. And this is talking about how to choose the pivot. So far, we have always taken the first element as the pivot, but we can choose it in a sort of smarter strategy. For example, let's take the middle one, or we can take even smarter, take the first one, the last one, and the middle one, and we take the median of the three. This is usually probably the usually the quite good solution. The only thing is, if you have this fixed strategy, someone who wants to mess up with you, they can come up with a workload that always creates a worst case scenario when you choose pivot in this way, if you spend a bit of time. So in general, we can just use the random function, which we will cover later in the semester, to pick a random number within the array that you want to partition next. And that's probably, in general, will give you a good performance on average sense. So far, so good. This is actually the random case. So in this process, when we say an algorithm to analyze the algorithm's performance, there's actually a few different cases. There could be when we analyze an algorithm performance, we can analyze what will happen in an ideal world when everything just falls into the right place. Or what will happen if none of this works, and someone is trying to keep messing up with us, then what will happen in the worst case? And somewhere in between, like practically, if you got an average sort of workload, what will the performance be? And we want to do this average analysis, we need to have this randomness stored in the way, like you need to have a data that has a sort of uniform random distribution. Even with this average case analysis that we have done so far, this assumes that the pivot appearing in each of the position of the element has an equal probability. If the pivot has a high probability, just keep residing into one of the positions, then this will not hold either. So for average kind of analysis, it needs a bit of randomness in there. Now, and when we design algorithms, usually we focus on the average case and the worst case. We do not care that much about the best case. For Quicksort, if we just add a quick scanning to test whether the array is sorted already, we can kind of guard us from the worst case. So we just go through the array, and if it's already sorted, then we don't do a Quicksort. That's the sort of best case scenario that we can do. And on average, it's n log n, worst case is n squared. These two are the important, and we're trying to guard our workload from appearing, from hitting this worst case scenario. And when we're trying to determine whether to use an algorithm or not, we're trying to look at the average case and worst case. Because, for example, we chose Quicksort over insertion sort because we know for insertion sort, the average case is just n squared, which is just the worst case of Quicksort. So obviously we should go with Quicksort rather than insertion sort. But in life scenarios, sometimes we think about sort of different optimization goals. For example, if you go for buy a lotto ticket, best case you can get 1 million. On average, you might got $10 expectation if you keep buying it for many times. And in the worst, you don't get anything. You need to think about whether you should really go for the best case scenario or average case scenario or worst case scenario. In this case, actually, probably you really need to focus on the worst case scenario because in most of the time, you're not going to get anything returned by buying lotto tickets, right? So this kind of best case, average case, and worst case analysis actually applying in many things, not just algorithm analysis. So that's sorting and algorithm analysis. So far, so good. Any questions before we move on to the next topic? So if you go to this set of slides, lect05.pdf, at the end it also have this link to the source code that we demonstrate, including binary search, Quicksort, and some. This is a skeleton code for you to implement your own sorting algorithm, the sort scaffold. And there's a few exercises at the end as well, which you should really do after class. And with that, we can kind of summarize and finish this chapter. So in this chapter, we show arrays and we show algorithms on arrays. And we also show how to show an algorithm is correct and how efficient an algorithm is. And in particular, when we show the efficiency of an algorithm, we use this big O notation. And importantly, big O notation is an upper bound. Remember, big O notation is upper bound. And because of that, an algorithm can belong to many different big O classes, big O complexity classes. And typically, we only use the one that is closely bounded closely bounding the actual complexity of an algorithm. When we do this analysis, we can have like best case, worst case, and average case analysis. And usually our focus is really the average and worst case analysis. And for Quicksort, importantly, on average it takes n log n time, but in the worst case, it can also fall back to O(n) squared time. When you decide whether to use Quicksort, you really need to sort of check your workload, whether it's a workload that have some sort of randomness in there. Otherwise, you might want to avoid a Quicksort. And later on in the semester, we're going to actually introduce a couple more sorting algorithms that doesn't really rely on that kind of randomness, and it can still achieve n log n time. So that's Quicksort and algorithm complexity analysis. The rest of the class is going to, including the second hour, is going to talk about strings. And we say that strings are no more than a special kind of array that are used to store characters. Except that there's actually something special there. For strings, this kind of array of characters, they have to end with a special sentinel value. Just like when Shannon demonstrated that. When you create an array, you can use a special value at the end. For example, -1 to indicate the end of the array, such that you don't need a body variable to tell you how many elements, how many integers have you stored in this array. Right? That's sentinel value. For strings, it's the same, except that it always requires this special value called a null byte. It requires a special value called a null byte. That's the reason why we call it a null terminated array of characters. Before we actually look at the example of these strings, let's sort of do a bit of motivation talk. Why do we need to use strings? The reason why I want to use strings is because if you think about all the information that we perceive every day, there are actually only two kinds of information. One is numeric, the other is text, symbolic, right? And so far, all of our analysis and discussion have primarily focused on numbers, process numbers, sort numbers, search numbers. But what about characters, symbols, strings? That's still also very important. And to process this kind of information, symbolic information, we need these strings. And in fact, if you think about nowadays, probably 10, 20 years ago, the buzzword is search engine, like Google or Bing search. That's the buzzword. And how do you make search engine work? And for search engine, it's really just about string matching, if you think about it. How do you match? Well, not really just about string matching, but a core problem is string matching. How do you match a user's search keyword with all the contents online? That's string matching, and that's actually going to be covered probably when Shannon's back. Now, another thing so that's 10 years ago, and nowadays, what do we talk about every day? We talk about ChatGPT, we talk about AI. Now, if you think about ChatGPT, if you haven't played with it, you probably should play with it a little bit. I don't believe I'm actually encouraging you to use that, but you obviously shouldn't use that for assignments or anything. If you think about ChatGPT, we actually incorporated ChatGPT into our ad discussion forum and let ChatGPT to answer your question. The duck in the ad discussion forum is actually a ChatGPT behind it. So it also produced all these strings. Well, you might think that it produces sentences, right? But sentences still strings. And the core idea behind ChatGPT and all this generative AI is essentially just statistical model. What it does is, given a sequence of words or strings or characters, it will predict what's the most suitable word to say after that. That's the core idea. So it's no more than a set of strings, and it predicts which is the most correct word to say next. And if you keep predicting the next word to say, next word to say, next word to say, at some point, you're going to form a whole answer to one of your questions posted on ad. And to know how all these things work, you have to know how to process strings in the first. And that's the reason why we are introducing strings in this subject. So far, so good. That gives you a bit of extra reason to learn about strings. The rest of the lecture really is just about how strings are represented and processed. There's really not a lot of algorithm stuff in here. You might thought it's a bit boring, but we have to sit through this part. And then I'll keep the fun stuff for Shannon to cover all these interesting searching algorithms and things. So this is what we're going to cover about strings. We're going to talk about the string basics. That's the topic of today's class. And after that, we're going to do string searching using some special algorithms called KMP. And then there's also this indexing structure for strings. What does indexing structure mean? Essentially, it's almost like the binary search idea. If you think about it, in order to run binary search, we know if you want to search something in a large pile of stuff, if the large pile of stuff is random, you have to do linear search. That's quite slow. But if you can do a little bit pre-processing, you order these elements or large pile of stuff, then you can do binary search. That pre-processing is actually a very common idea. If you can do this kind of pre-processing, then you might come up with a sort of way of organizing data that will help your later processing of data in the long run. And that's called pre-processing. And if you come up with a special structure on your data, that's called an index structure. And we are also going to cover like special structure for strings, such that will enable our searching of the strings a lot faster than just do a online searching. Because in the first lecture, you already seen that find the repeats. If you just go through each of the characters and try to find repeats, it's going to be very slow. But if you can do a bit of pre-processing to organize your strings a little bit, it's going to be a lot faster. So that's going to be covered in this chapter. And in today's class, we'll probably only cover this bit, the basics, not really to any of this searching and interesting stuff. So we just say that strings is no more than a null-terminated array of characters. What is that null-terminated character? We'll see that example very soon. Before that, we just also need to quickly mention that because strings are essentially just an array of characters, all the string operations, they are actually processed in the form of a sequence of characters. So there's actually no, for example, adding two strings together. That doesn't really work. Whatever you do on a string, essentially just go through each of the elements in the array representing a string, and you do some modification. That's the general idea. And the C programming system actually provides some library function to support those kind of processing. In particular, there are two libraries called CType and string. CType offers operations to handle characters. String offers sort of functions to operate on strings. And here's a couple of examples, and we will demonstrate these examples along the lecture. Later on, when you learn what we call memory allocation, which is a way to create variables of dynamic size. So far, all the variables that we create, no matter sort of int or an array, once they are created, their size are fixed. We cannot change that. But later on, when we have covered this memory allocation mechanism, we are going to be able to create items of changing size during the running of a program. And by that time, we are going to be able to create strings of sort of varying length. So let's look at a string example. What do we mean by a null by? Here is a string example. As we just mentioned, a string is just an array of characters. And here we exactly create a string in an array of characters way, except that at the end there's this special character, what we call a null by, that indicates that this is the end of the string. Slash here is what we call an escape sort of character that tells that this is not really the zero character, but a special character called a null by. And if you still remember the ASCII code that Shannon also mentioned that earlier, say every character in the end is stored as an integer in the system, right? And that integer is the ASCII code of a character. Now for this null by, it has a special value. It has a special ASCII value, which is just 0. All these other characters, for example, if you want to put a character 0 actually doesn't have a 0 value corresponding to its ASCII value. For 0, I think the value is probably 48 or something for its ASCII value. I might have remembered it wrong, but it's not 0. /0 is really 0. And when a system processes a string, what it does is basically just go for a for loop and keep looping until it hits the null by, which will tell you that this is the end of the string. So that's what null by does. And it's really important to know that even though we say null by is not really part of the content of a string, it still counts for one place in the array. So in this case, I created an array of 10 characters, but here I'm actually storing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Even though this is not a content character, it's still counted as a character. So I'm actually going beyond the boundary of the array. And let's see what will happen if we do this. And if I do that, system will show a warning. GCC here is just another version of CLang, a compiler. So Shannon used CLang, I'm using GCC, but it makes no difference really. So system tells that there's a warning. We are going beyond the boundary. We have excessive elements in this array. Array says I can only hold 10 elements. I'm giving it 11. There's a warning, but doesn't really matter. I can push forward and run it. If I run it, you can see that the print statement in here still works. And to print a string, you use %s and put the string variable name in here. Print it, except that there's this extra character which we never really put into this array. And that's what will happen when you put a string that doesn't have a null by in a proper place. The system will keep going and going and going until it sees a null by. And apparently, we don't really have a null by. In this case, the C language standard says if this happens, the behavior is undefined. And in this undefined behavior, it gives us a random character to print out in here. So be careful. The null by also counts as one space in this array. So if we want to make it right, we have to, for example, remove one of the letters in this array so that we don't go beyond the size of 10. Make sense? And let's try to run that. And now it works, and there's no this random extra big letter E in here to print out. Now, once we created a string, we can actually change its elements. For example, I can change its first element, and to change its first element, all that we need to do is just like what we did for integers. If you want to change one of the integer element in an integer array, what we did was just to take the array name, and we take the substitute index of the element, and we put a new value into it. That's what we do. And I can sort of try to mess up with the system, and I'm again going beyond the boundary of the array, and let's see what will happen. Oops. From compilation perspective, again, it will give you a bit of a warning. It says that you are going beyond the boundary. You said you want to go to the 80th element in the array, but the array size is only 10 when you declare it. It's a violation. But maybe you know what you do, so the system will not sort of stop us to do it, and we can run it. And actually it still works, but it's very dangerous, because now I actually don't know what have I changed in the memory. Because this string 80 might be a piece of memory that belongs to some other program. It could be the time card that I'm just trying to approve for one of our teaching fellows. The very modern computers, yes, you are right. All this memory, they're actually separate from each other. But in older generations, or maybe in some of the older servers, it could happen. Yeah. Obviously, my example is a bit of an exaggeration to sort of tell you not to do this. Yeah. But you're very right, you picked that up, yes. In modern computers, actually, no matter what you do, all you do on your program, it only sits in your program. You cannot really touch anyone else. And that's the reason why when you write a piece of C program and you are not sure what will happen if I do something, then just do it and try to compile and run it. Doesn't really matter. At least on your own laptop, nothing is going to break. It's not going to break your program. It's not going to break anyone. It's not going to break the whole internet. Don't worry. Just try it. So that's what we are talking about in here. So in any case, don't do something like this. We already know that this wouldn't work. Now, there's one more thing to talk about. As we keep saying that, for strings, the null byte is the signature of the end of the string. So what will happen if we put a null byte in the middle of a string? What do you think will be print out if I organize this string in this way? Make a wild guess, please. First three letters H. Let's try that. And very good. So indeed, only the first three letters got print out. Now, again, we repeat this. Whenever you have a string, and no matter whether you are writing the function or you're just calling a system, well, when you're writing your function, you can determine where to end. But if you are calling a system function to process a string, the system function will keep trying to look at the first null byte. Once they see the first null byte, the processing will stop. Now, I can have another null byte at the beginning, and just to make sure that we don't go beyond the boundary of the array. For example, in an extreme case, I'm putting a null byte at the beginning. Let's see what will happen. Oops.
Change that to H.
Sorry?
If you change the first letter.
Right. Very good observation. That gave him a heart attack. And nothing got printed out. And with that, we will sort of put a pause in here, and then we'll take 5 minutes break, and we will continue the discussion about strings in the second half. So come back in 2:56. All right, let's continue the discussion on the string basics. For those of you who want to run away, now is the time to run away. If not, we will start, and then you can't just go away in the middle of the class. So we talk about strings, how to declare a string, and how to modify a sort of one or two element of a string. Now, next, let's look at how do we read a string. Like for integers, we know we can do reading a string using scanf statements. But how do we do that for strings? Now, to do that for strings, it's pretty similar, I would say. We still call the scanf function call, and this time we use %s to tell system that now we want to read strings. The only difference in here is really that, you know, if you want to read an integer, we always put an ampersand in front of the variable name, right? But for strings, we don't have to put the ampersand, and actually we should not. The reason for that is because the scanf function call essentially is to take a pointer pointing to a variable such that it can feed the value into that memory address, such that you can get the value read. Now for strings, it's already an array, which is already a memory address. So we don't need to put another ampersand to take its memory address. The string name itself will serve the purpose. So don't put an ampersand in front of string name in scanf function call. Let's try to compile and run this example. So if you run it, I can put some random things into it, and it will record that. Doesn't have to be characters. We can put like uppercase letters, and we put numbers. I can put like special symbols. Oops. I can put like special symbols. It will all work. The only thing that wouldn't work is if when I put space into it. If I put a white space, only the content up to the first white space will be captured by the scanf function call. So if you really want to read a piece of text that are like containing white space, you cannot use scanf function. Have to use a different mechanism, which we will demonstrate. If we have time, we'll demonstrate that in the later part of the lecture. But for now, just remember, using scanf function call, you can read only up to a white space character. So far so good. All these are just like processing techniques to work with strings. There's really nothing magical in there. You just have to be aware of that. You can do this, and you can not do that. And you have to play with this to get used to all these sort of rules of what you can and cannot do using strings. Let's see one more example. So what we are going to demonstrate in this next example is a loop to loop through the elements of a string, and to show you what will happen if we start the processing in the middle of a string. So in this case, what we are doing in here is like, let's go through from element 0 up to the element where there's a null byte in there. Just starting from the beginning up to we hit the null byte. Now, for every element that we look at in each iteration, what we are going to do is that we're going to print out the memory address of each element, and we are going to print out the string starting from the middle element of the, which is sort of part of the string. Because here, the first printout we use %p, which is to print out the memory address. Second one we use %s, which is to print out a string. But here we are starting from the middle of the string, and let's see what will happen if we start printing a string from the middle of the string. And the last one, the printout is just the element at that particular position, which is just a character. And for that we use a %c for the purpose. Let's see what will happen. And so we know the initialized string is just hello, and in each iteration, I'm going to start from a different position of the string. The first one is starting from the 0th position, second one from the first position, and second position, so on and so forth. As you can see, after each iteration, the memory address got increased by 1. So it's going through one after another, and these are the memory address for characters. For every character, it takes up 1 byte. So the memory address got increased by 1 after every iteration. And the printout starts from each of these letters in the middle, and it continues until it hits the null byte. So it will always print out until it hits the ending character, which is O. So this again reinforces the idea, when you pass a string into a system function call, it will start processing from the memory address that you give it to it. For example, in here, we are giving the memory address starting from this middle character H, and the processing starts from the middle H, and then it keeps printing until it hits O. Now, the last printout, which is just one single letter, in here, we are just printing out one of the letters in the string. So far, so good? Yes?
Why, I'm still not sure about why the characters only take up one bit space.
Sorry?
Why the characters only take up one bit space?
Why the characters take out only, it's not 1 bit, it's 1 byte.
So it's 4 bits.
8 bits.
Oh, okay, got it.
Every memory address is copying to 1 byte. Let's look at the sort of, so this is sort of a plot of the memory tape, and the memory tape got cut into basic units. Every basic unit is a 1 byte, and every basic unit is correspond to 1 integer, which is the memory address of that byte. So this is what's going on. So after every letter, the memory address got increased by 1.
Why wouldn't it become a number? It takes 4 bytes each time.
For integers, it has to store, for integers, it has a larger value range. You need a larger storage box for that. Characters, if you think about it, for characters, how many different characters do you know? On the keyboard, typical keyboard is like 100 keys, right? Give or take. For 100 keys, it corresponds to an integer from 0 up to 127. And that's enough, 1 byte is enough to represent that. But for integers, like for an typically you go from 0 up to 2 billion. That cannot be handled by just 1 byte. So it takes 4 bytes. That's just it. So that's how to process a string. We can, because we say a string is just a pointer, so we can also process a string in a pointer way. Now, in this next example, what we are demonstrating in here is that, well, let's assign this array pointer, well, this array name, which is a pointer, to a character pointer. So, because a string is just an array of characters, which is a memory address pointing to a character that leads to the rest of the string. So we can also use a character pointer to point to the same starting place. once we got this pointer pointing to the same place, we could repeat what we have done. We could repeat what we have done with the string now, except that we use a pointer. Now, when we do this star p, it will tell you that when you do this star p, it will tell you what is the value of the current character. P itself is a memory address pointing to a character, but star p is the actual character in there. So we can pretty much repeat the same experiment like before, and we can compile and run, and the output will be exactly the same as before. Only that now we use a pointer variable to process a string rather than the string variable itself, but they work the same. So far so good. Yeah. Okay, so that's the part. The final thing we want to mention about this string is that so far we create a string in a really cumbersome way. We actually write up every single letter of this string in an array of characters. The C programming language actually offers a little bit of sort of language sugar, syntax sugar, that allows us to create string in a simpler way. Here is a few examples of that. We could create a string. We could create a string. Just write a string in a pair of double quotes. This creates a string, and we can assign that to an array of characters. This will create a string, and a null byte will be added to this letter, to this array of characters by the operating system. So when you create a string in this way, you don't have to add this. You don't have to add the /0 at the end. Oops, we missed that actually. When you create a string in this way, the /0, the null byte, will be added by the system by default. So you don't have to worry about that. Now there's another way which says, let's just create a string and assign it to an array of characters. In this case, the system will automatically figure out what is the size needed to hold this whole string, plus the null byte. So you don't even need to put a size of the array in here. A third way is to create it in a sort of pointer way. You can do this as well. Now, these first three ways, they are pretty similar, except probably the size in here, you have to work it out, or the system work it out for you. The last one in here is actually a bit of different. If you create a string in this way, this is complications in that you cannot change the content of the string. This is what we call a constant string. If you create it in this way, and if you're trying to change the first element of the string, let's see what will happen. You're going to hit a bus error. If you create a string in this way, it's actually resides in a special piece of memory that is not supposed to be changed. If you really need to create a string and another string that starts from lower letter h, you have to create two separate strings. You can't create one and then change it in the middle. In fact, if we're trying to run this piece of code, so now I've fixed this one such that I don't change this content anymore. I'm just printing as before. And if you observe this memory address, you will see that this new way of creating this string in here has a substantially smaller memory address than the previous way. And this substantially smaller memory address corresponding to a special piece of memory that is not supposed to change during the running of the code. So that's what's happening. So far so good. So that's how to create strings, how to sort of print it out, you values into it, process elements. The next to cover is how to put strings into function calls. How do we write a function to process a string? In here, we give an example of writing a function that copies one string into another. Now, we say a string is just an array. So if you want to write a function that processes strings, you basically write a function that processes arrays. And obviously, you can also write a function that processes character pointers. Both ways are fine. So far, you might have seen function prototypes that always give you a sort of variable name as well. And then we can add it back. but these are essentially just optional, because from the compiler perspective, all that it needs to know is what really is the function name, what kind of things it's going to take into this function call, and what kind of things it wants to return. So the types of these things are enough. From the compiler perspective, what exactly is the variable names in here doesn't really matter. You are going to supply the actual function name in the function body here anyway. So with or without this des or source variable names in here, the piece of code will work and compile. And just to sort of minimize confusion, I'll just put this source and destination in the prototype declaration so that you're not feeling too confused. So this string copy function example that we're showing here, what it does is to take a string, what we call the source string, and we're going to copy its content to a second string. We call it destination string. That's what it does. And in the main function, we are creating two strings, string and another string. Each of them can hold 19 characters plus a null byte. And we are going to copy this text1 string into the first string. And we're going to repeat the copy test2 into the string. And we are going to repeat a bit of extra copying in here, but let's not worry about it. Just focus on this bit first. And I've actually copied this piece of code onto the code demonstration process again. Now, if you run this code, as we just say, we're going to create two strings. Each of them can hold 90 characters plus a null byte. And I'm going to do this copying, and let's see what this string copy function does. And obviously, it takes two arrays into the function call. And as you can see in here, when you put an array into the function call, this function call actually just got a pointer. It doesn't got a copy of these two arrays. It got two pointers. The first pointer points to this destination string, which is, we say we want to copy this content into a string. So this string in here becomes our destination string. And the source string, test1 in here, actually is stored in a special piece of memory. This is actually another example of a string that is stored in a special piece of memory. And for this one, again, this one is also an example where we actually cannot change its content. Reading and copying this content is fine, but for this one, again, we cannot change its content. So you got a pointer that points to this special string, and we're going to do the copy place. So we're starting from obviously the first element, and we have a while loop that says, while we haven't hit the last element of the source string, keep copying over. This basically just keep copying over and move to the next character. So if you run this one, it's just one character at a time, copy over to the destination string. And because we say strings are arrays and arrays are pointers, this copying over, the content got copied over, actually can reside in the string that we created in the main function, even though we are now processing that through a pointer inside a function, not really the main function. So keep doing it. Now, I should actually go back a little bit. Now, the really important stuff in here is that when the while loop finishes, there's one thing missing in the copying process, which is the final null byte. And the reason for that is, if you look at the while loop, it says, while we haven't hit the null byte, keep copying over. Once you hit the null byte, the while loop stops. And because of that, there's no null byte for this destination string. The source string, we have a null byte, even though we create it, just write it in a pair of double quotes in here. We say that system will automatically add that null byte at the end. But in this copying over process, we didn't have the null byte because the while loop says once we hit the null byte, stop. And this is actually a common issue when we process strings, because we say when we process strings, we keep checking for whether we hit the null byte or not. Once you hit the null byte, don't do anything further. But sometimes we actually still need to do something. In this case, when this string is done, we actually need to still add a final null byte to the process. So we have an extra statement to say, well, let's add a final null byte to the destination string to complete the process. So now the final the copying finally finished. This is actually all that we need to do to copy one string to another. There's an additional statement that says, all right, let's also return the destination string. Why do we want to return the destination string? We really don't have to, because the copying over is already done, right? And the reason why it's still returning the destination string doesn't really mean that we have to return this such that the main string in the main function will get this piece of value. Not like that. The string in the main function already got this piece of value. The reason why we want to also do this return statement is only such that we can mimic the assignment operator. Because if you think about the string copy function, it's essentially like assigning a string to another, right? Here we are assigning test1 string to this string variable. Now, if we talk about assignment operator, think about an integer case. If you're assigning, if you're assigning a value to an integer variable, you can actually put these assignment operators together to chain them together such that you only have one statement, but you can assign a value to multiple variables. Now, using this return statement in here, we can mimic the behavior. We can say, let's copy a string to a string. And the return value, I'm going to use that to copy to another string. So such that we can put this string copy function call into one single statement and you can copy over many different strings. Still, there's really no point to do this. In my career so far, I've never really done something like this. But that's how the system function has been designed. So here we are just basically show you string copy is actually a system provided library function that copies one string from one string to another. Here, our implementation just to mimic this one. And in the library function, it says, let's return the destination string pointer. So we also return that. But in practical use, there's only minimum to use this. Now, there's something special in here that says const. What does this const mean? We didn't use that in our code. This const means that I am not going to change the content of this string pointed to by the second pointer. Because we are just copying over from the source to the destination, I'm going to change the destination but not the source. So I'm going to tell you, I am not going to change that. Const means constant, so I'm not going to change that. That's just all that it means. Yes?
What if the destination string is shorter than the source string?
Very good question. Question was, what if in this piece of code, if I don't have 20 characters space created, if I only have a string that can hold 2 characters, then I'm trying to copy a long string into a short string. It's going to be a memory access violation. Because in the copying over process, as you can see in here, we never really check whether we have hit the boundary of the destination string. We just keep copy over, and it will go beyond the boundary. And that's a dangerous process. In fact, when you call these string processing functions, you should always sort of make sure that you have enough space before you proceed with all these string editing operations. So far, so good. Now, there's an alternative implementation that is shown in here that uses a pointer way to do the process. Now, it looks very complex. We are going to demonstrate you step by step how do you go from an array implementation to a pointer implementation that looks really weird. So if you want to do this string copying using pointers, you can write a function header like this, and you can use exactly the same array process to process these 2 strings. Even though you take them in as pointers, you can still do this in an array way. Nothing wrong with them. In fact, if you can do it, we're very happy for you to do it. You don't have to use pointers in this particular case. But how do we go from this implementation to a pointer implementation? Here's how we go. So we know this destination I and source I is essentially a language sugar, right? This is just source plus I. This is just syntax sugar, so we can convert that to a pointer. We can convert it to a pointer way. And similarly, for this source, we can also convert it into a pointer. And for the destination, we also convert it into a pointer. That's the first step to convert from an array to a pointer implementation. Now, using pointers, we know we can do pointer arithmetic. Actually, we can also get rid of the I. So how do we get rid of the I? What we can do is, let's not worry about it. Let's look at this source pointer and see where it points to, and just copy over that. Now, once we've copied over what source is pointed to, what we need to do is now move on to the next letter. And to move on to the next letter, we're going to say, let's change the pointer a little bit. And that's how we get to the end here. We also don't need this one anymore. Make sense? So far, so good. Just copy over one letter and then increase the pointer such that it points to the next letter to be copied over. That's the process. But still, this one is still a bit far away from that one. Now, what's happened next is that, so this plus plus operator says, let's increase the pointer by one step to the next one. We can actually put the plus plus inside. Why can we put that plus plus inside? The reason for that is this plus plus is what we call a post-increment operator. What it does is when the whole statement has been finished, increase the value of source by 1 and then increase the value of destination by 1. So when we write a statement like this, what will happen is let's take the value at source first, assign it to the value at dest, and then increase that by 1, increase source by 1, increase destination by 1. That's what's happening. That's what's happening in here.
I think it's less readable. It's less readable.
Definitely less readable, and I'm not going to recommend you write a piece of code like this. I'm just trying to show you that if you see a piece of code like this, what does it mean? And some programmers actually like to write a piece of code like this because it's short and succinct, and they like it. I personally don't write code like this. So that's how we can do it. Now, we can make it even more extreme. So we know, if you go back to this assignment operator, so after this assignment operator in here, we know that we assign 1 to B. And this 1 can be continued to be assigned to A. So same here, if I put this statement inside of a while loop, if I put this statement inside of while loop, I can actually assign this one to that, and then the return value of it, we can test whether it's null or not. So I can do assign this one to that and test this assigned value equal to 0 or not. And we know to test whether a statement is equal or not, I don't really need to put it in here because the while loop itself already tests whether the condition is true or false, right? So I don't even need that. So this is all that I need. And I don't need anything in the while loop. That's how we go from this array implementation to this pointer-based implementation. These parentheses here can be removed. Doesn't really matter whether we got a parenthesis or not. And importantly, if we do this way, you will keep assign, and test, assign, and test, assign, and test, assign, and test. And the important thing is, it will assign and then test. Because of that, even the null by we got assigned, and we don't need the extra null by setting statement. The only thing left is that here in this case, it uses an actual pointer p. The reason for that is, remember, at the end of the function call, we want to return the destination pointer. If we keep doing this, we actually keep updating the destination pointer to the end of the string. We don't want that. We still need to be staying at the front of the string. So instead of using the destination pointer, it uses an actual pointer called p, and in the process, only change p but not the destination pointer, such that the destination pointer remains where it was. That's the process. Yes?
If you make the source pointer const, will it let you increment it or not? Because it's a constant then.
Oh, the constant there means the content in that string cannot change. Pointer can change. It's very weird, but actually here, if you look at this definition, there are actually 2 ways to write it. If you put the const in front, that means you cannot change the content, you can change the pointer. I think you can swap them. You say char.const, then the pointer itself cannot be changed. Yeah. That's the weirdness about C program language. Don't worry too much about it. These kind of details you probably will never hit it in your whole career. So don't worry. So that's how we write a function to process strings. So far so good. Fall asleep already. So to cheer you up, let's actually play a video to show you how Google search works. I'm not their ambassador. I have nothing to do with them. It's just a motivation sort of video to show you what you can do using these kind of searches. If anything, I should vouch for Bing because I've actually been an intern with Microsoft for a few months. I have nothing to do with Google at all. But it just shows you how Google search works and as a motivation to study strings.
Every day, billions of people come here with questions about all kinds of things. Sometimes we even get questions about Google search itself, like how this whole thing actually works. And while this is a subject entire books have been written about, there's a good chance you're in the market for something a little more concise. So let's say it's getting close to dinner and you want a recipe for lasagna. You've probably seen this before, but let's go a little deeper. Since the beginning, back when the homepage looked like this, Google has been continuously mapping the web, hundreds of billions of pages, to create something called an index. Think of it as the giant library we look through whenever you do a search for lasagna or anything else. Now, the word lasagna shows up a lot on the web. Pages about the history of lasagna, articles by scientists whose last name happened to be lasagna, stuff other people might be looking for. But if you're hungry, randomly clicking through millions of links is no fun. This is where Google's ranking algorithms come into play. First, they try to understand what you're looking for, so they can be helpful even if you don't know exactly the right words to use or if your spelling is a little off. Then they sift through millions of possible matches in the index and automatically assemble a page that tries to put the most relevant information up top for you to choose from. Okay, now we have some results. But how did the algorithms actually decide what made it onto the first page? There are hundreds of factors that go into ranking search results, so let's talk about a few of them. You may already know that pages containing the words you search for are more likely to end up at the top. No surprise there. But the location of those words, like in the page's title or in an image's caption, those are factors too. There's a lot more to ranking than just words. Back when Google got started, we looked at how pages linked to each other to better understand what pages were about and how important and trustworthy they seemed. Today, linking is still an important factor. Another factor is location, where a search happens. Because if you happen to be in Ormea, Italy, you might be looking for information about their annual lasagna festival. But if you're in Omaha, Nebraska, you probably aren't. When a web page was uploaded is an important factor too. Pages published more recently often have more accurate information, especially in the case of a rapidly developing news story. Of course, not every site on the web is trying to be helpful. Just like with robocalls on your phone or spam in your email, there are a lot of sites that only exist to scam, and every day scammers upload millions more of them. So just because instantvirusdownload.net lists the words lasagna recipe 400 times, that doesn't mean it's going to help you make dinner. We spend a lot of time trying to stay one step ahead of tricks like these, making sure our algorithms can recognize scam sites and flag them before they make it to your search results page. So let's review. Billions of times a day, whenever someone searches for lasagna, or resume writing tips, or how to swaddle a baby, or anything else, Google software locates all the potentially relevant results on the web, removes all the spam, and ranks them based on hundreds of factors like keywords, links, location, and freshness. Okay, good time to take a breath. This last part is about how we make changes to search, and...
Enough. Wake up now. So now in order to make that work, there's a lot of advanced sort of searching and ranking algorithm in there. Actually, the searching bit is like Google is well moved beyond about the searching. And the search engine at the current stage is really about ranking, how you can rank the most relevant result at the top. Searching is not a problem, right? For them, it's really how you scale an algorithm. They can do this search really fast. But once the search is done, how they rank this result is really the crucial part that they retain their customers. Now, in our case, we will just start with talking about how to build this searching part. We are not at the ranking part yet. For the ranking part, nowadays everybody is using machine learning, AI, and other stuff. That would be, again, another subject. So how do we do this search? Now, in order to do this search, we need to do a matching. We need to match words, right? If you have lasagna, we have to be able to find out in a particular piece of document that contains the word lasagna. So in the first place, we need to fetch everyone this document and we cut them into words. So we know that that document has a word lasagna. How do we do that? And here we are going to demonstrate an example how to achieve that. And now we are sort of moving on to a bit more practical scenario, not just the basics of the strings. Now we are talking about how to cut a piece of document into strings. This is still an example to show how strings work, but hopefully it feels a bit more practical. So to cut a piece of document into words and then store all these different words, all these unique words in a document, obviously the count, the frequency of words also is important in terms of the search engine scenario, right? For a document that mentions a lot of Nasalian, that's probably a bit more relevant than a document that only mentions Nasalian for only once, right? So the count also is also important, but in this example, we just focus on cutting the words of a document out and keeping only the unique ones. Now, how do we cut the words from a document? That's going to be, probably we don't have enough time to do that, but we will assume that we have a function that can cut a document into words, and that's probably, we can rely on Shannon to tell you how to do that cutting. We are just focused on, if we have a function that can cut document into words, how do we manage them, and how do we only keep the unique words? In this case, in order to sort of store a set of unique words, what kind of facilities do we need? What kind of variables do we need? What do you think? I have a document, I have many words. Every word probably is a string, right? We have learned that. Every word we can store it with a string. If we have multiple words, what do we use to store them? Yeah?
Like a 2D array, like a string of strings.
Yeah, an array of strings, a 2D array of characters. Very good. That's what we need. We need a 2D array, and assuming that we can only allow this maximum number of words, could be, let's say, 1,000 words in a document. Could be 1 million, doesn't really matter. And each word can allow this maximum number of characters. For example, 50 or 10. Also doesn't really matter. It's a constant that we come out and we can change that. So we need a 2D array, and in the memory it looks like this. Well, not really like, but conceptually it looks like this, a 2D array, like a table. In memory, obviously, everything is just a linear long tape, but conceptually we can think of it as a 2D table. Now, here we are assuming that we got an array that can store up to 100 words, and every word can store up to 10 characters plus a null byte. And we will need a separate variable, a single string, to store the next word that I have just written, one word. And we assume that there's a function that can cut this piece of document into words. So at the start, this one word will store this algorithms word. For example, this is our document. Algorithms are fun, although our tests are not. So we're going to cut it into a sequence of words. We'll get the first word, and we're going to copy that into here. And we will repeat the process. We'll repeat the process, and each time when we get one more word, we are going to put it into this array of all words. But how do we keep track of where this new word to be put in? For example, after we've done with the algorithms, we are going to process a word called R. Where do we put R in? Apparently, we'll need another variable to keep track of how many distinct words that we've written so far. So at the beginning, we only got 0 distinct words, and we're going to put it in all words 0. Right? So that's the reason why algorithm we got put in here. Now, when that's done, we are going to increase this looping variable I by 1, or we're going to increase the number of distinct words by 1, and then we can put it into the second one. And then we put it in the third one, and fourth one. So we basically, every time we got one more word, we increase the number of distinct words in my array of all words by 1, and keep appending more words into it. That's the basic idea. The only we can keep doing this. Now is sort of the tricky bit. We got algorithms are fun, although our tests, all these are unique words. We can put it in. The next word would be another R. Should we just put it at the end? We shouldn't, because it's repeated. But how do we know whether it's repeated or not?
Compare with all existing.
Yeah, we need to compare with all the existing ones, right? And for that, we need a loop. This is a looping variable. So this string copy is a function that we keep appending the new element to the end of this all words array. This strcmp, string comparison, is keep comparing the new word with all the existing words. And in fact, this part actually needs a loop, not a single pair of statement. We need a loop. We need to compare. When we're looking at R, we need to compare, are you R? Are you R? Oh, yes, you are R. Then I'm going to stop. I'm going to not put this new R into here. And I'm going to skip that and move on to the next word. And so there's actually a little bit of algorithm in this case, which is a linear search, and make sure that a new word doesn't match with any of the existing words. Let's look at the implementation of this bit of process. So this is essentially a copy over of those variables that I declared and showed in the lecture slide, in the Excel sheet. We got this word. We say this all words has this can store up to this maximum number of words, except that now you don't see the number of characters, maximum number of characters. The reason for that is because now I'm actually not creating an array of characters. I'm creating an array of words. And every word itself is an array of characters. So we now actually use a type def to create a hierarchical definition of types. All words here is actually an array of words, but every word itself is an array of characters. So essentially, this is just the 2D array that we created in the Excel sheet. We got a number of non-distinct variable to keep track of how many distinct words we've read so far, unique words we've read so far, and total words records all the words, counts all the words we've read so far, whether they are unique or not. And there's some looping variables and some flag variable to keep track of whether this new word can be found in all the words that have been written so far. The getWord function is a function that is in charge of cutting the piece of document into a piece of words. Let's not worry about it so far. Just assume that it will work. And it says that let's keep reading reading the next word into this one word variable. One word is an array that can be used to store one next word. Keep reading that, and we only allow maximum chars, that number of characters, to be reading one word. While we haven't hit the end of the file, EOF is a system special constant that indicates the end of input. EOF is short for end of file. File in here could be like the input file, could be actually a document file. So, but in general, it's a signature that signifies the end of input. While we haven't hit the end of input, then we have another word that we read in, and then this piece of code is to check whether this new word can be found or not. At the start, we'll assume that it cannot be found, because I haven't looked at anything yet. I haven't found the new word in my existing list of words, so not found yet. 0 means not found yet. And I'm going to use a loop to loop through all the words I've found so far, that I've put in this array so far. So the looping variable, I will loop through the first string, second string, third string, so on and so forth, up to the end of all the existing strings. Then the end of all the existing string is indicated by the non-distinct. This is the number of distinct words we have reading into my all words array so far. While we haven't hit the end, and while we haven't found, so exclamation mark here means not. While we haven't found this new word in my existing array of words yet, keep doing. So we keep going and keep going. And here, we're going to use this comparison function to compare the new word that we read in and one of the words, the ith word in the words that we already read in. If the comparison function returns a 0, meaning that the two string matches. If the two string matches, this is a logical statement. If the two string matches, then this statement is true. And it will make this found to be true. Here it says, while not found, keep going. Once it's found, the for loop will end. When the for loop ends, we will say, is it found or not? If it's not found, and we haven't hit the maximum number of words we can store, then let's store it. And to store it, we're going to copy this new word into this all words array. And then I'm going to increase my number of distinct words that we found so far by 1. That's that. Here we got a linear search process, a little bit of algorithm in here to make sure that the new word we read in is not repetitive. This is how we cut all the words into into our array of words. And you might think that this is simple, but with a little bit of modification of this example, it can be used to sort of build up the first step of a search engine, in the sense that once we got all these words, right? Once we got all these words, we can actually run, for example, quicksort or insertion sort algorithm to sort these words. Once we got a sorted sequence of words in my document, now when a user comes and want to see whether there's a search keyword that matches one of the words in this document, we can run a binary search to match a search keyword with all the words in my document. And that's the way to make a fast search to match such keywords with words in a document. Obviously, this is still not really fast enough, because if you think about there are billions of documents out there. If you have to match every document, and even if a binary search is quite fast, you have to run a binary search on every 1 billion document to match a keyword, is not fast enough. So we'll take even faster steps, and that's going to be covered when Shannon's return. And I'm pretty much going to sort of stop in here, except that before we go, I just want to quickly demonstrate how this one runs. If I run this example, oops. Comparing, right? There's a bit of warning, but don't worry. Run it. It's going to wait for me to type in the string that I wanted to sort of cut into words. I'm going to just put in this piece of string, and it's still waiting for me to give them the end of file signal. And to give the end of file signal, I'm going to press Ctrl D. And it can correctly identify these are the words that I gave it, exactly just the same as I'm showing here. There are no two R's, even though the input has two R's, but the output has only one R. Now, similarly, we can actually use this words program to look at the unique words in my words program. So the left angle bracket is what we call the input reduction. What it does is to use a file to pretend to be the terminal input of my program. So let's see, if I run it, you will tell me that there are 106 unique words in my program, this program, and you can see it says that break the input up into a sequence of words. Let's break the input up into a sequence of words, and it can correctly skip the /* and all these like non-English letters. But how does it do that? We'll wait for Shannon to tell you the magic, how it cut a piece of document into words and only keep the English letters. That would be all for today, and then pretty much I think that would be all for me to show up in the lectures until probably the end of the semester. I might come again to say hi. But otherwise, yeah? Complexity? This is just linear, you have to go through them. So there's nothing magic in there. Right, that's all for now. See you later. Enjoy the holiday.